Sorry, please proceed.
Okay, there. So I will be talking today about some of the project that we have been working to.
By the way, sorry, what is the meaning of ripsaw?
Okay, so this is the code for the grant for Richard. So I guess like Richard is going to tell a bit more about it. So it's like the research in the propagating solar alpha waves.
Okay.
So it's a code of the.
That's a great acronym.
Yeah. So, so it's all it's the Richard's grant. That's what pays my salary. So to be able to.
Please go ahead. Sorry,
Yeah.
I had to know that.
So now we have a kind of a common consensus that like the coronal heating and the acceleration of the solar wind are not two different problems, but are a coupled problem. So like the answer to both of the problems may be one common physical mechanism. So a few models that actually deal with these kind of problems is the Alfvenic wave-driven turbulence models. So these models were in the kind of business for quite some time. And what these models are actually being having the key ingredients is that the Alfvenic waves are being generated in the photosphere at the foot point of the magnetic flux tubes. And these waves do travel along the magnetic fields. And they can just from the photosphere, they go across the transition region to the corona, even into the interplanetary media. And as these waves will travel, they will encounter the gradients in the magnetic field as well as the density. So whenever these gradients are in there, that can actually result into the turbulence, and the turbulent cascade is going to generate eddies. And those eddies are going to scale down to smaller scales where the actual dissipation of the energy is going to happen. So the very simplistic expression for that, which is being generally used in these models, the volumetric heating rate, is given in here. So where the Q is actually the expression for the heating rate, rho is the density, C plus and C minus are the Alfvenic variables. Alfvenic variables are basically the combination of the velocity as well as the magnetic field fluctuations. And one of the other parameters in all these models is this L perpendicular. So L perpendicular is the perpendicular correlation length scales. So what exactly? So and that's exactly what we were trying to estimate in our project. So what exactly is this L perpendicular? So the perpendicular correlation length, bit from the history, is like being used extensively in the stellar physics and as well as in the solar wind. So solar wind people were being using it for quite some time. So what this parameter actually tells in the model is basically how much is the magnitude as well as the spectral location where the heating should happen. So this is basically telling the scale of the biggest eddy that is going to form, and that particular eddy is going to break down to smaller eddies until we get into the dissipation scale. So it basically doesn't tell how much heating is going to happen, but it can actually tell how much energy we can be able to put into the environment that is going to end up into the heating. Now, again, it has been used for quite some time into the numerical models that have been dealing with the coronal as well as the in situ kind of things. So in the in situ, this particular parameter helps into the acceleration of the solar wind parameter, so solar wind velocities and stuff. But in the corona, it is actually telling more about how much the heating we could have. So you can actually, so there was no kind of an agreement what exactly the values for this particular parameter should be. So there were a few examples of these particular models. They use values from, let's say, in the photosphere from the 0.1 to 1 megameter, which is basically the scale between the two prime points, the distance between the two prime points. Again, some of the models from Chandra and Holweg, they kind of use like the L perpendicular could be around the 5 megameters. Again, at the photosphere, while some of the model at the base, like at the transition region, they use between 10 to 35 megameters. So again, there was not a kind of clearly defined what exactly this particular parameter should be. And all it was being used like depending upon what exactly you want to get out from your model. And this is being done for quite some time now. So before I kind of like dive into how we actually got into this particular estimation, here's a kind of a brief overview. So Richard has already given a very good kind of an overview what exactly the waves and propagating waves into the corona. So what we can see from the Trump observations is like the A is that the corona is inhomogeneous. So again, we do have the fine scale structures, which are like the loops and the open field lines, and they do have the kind of the variability from the 200 to 1,000 kilometers. And these kind of structures do exhibit the transverse motions. And these transverse motions, like as it showed, was like being observed into the intensity, which gives often an impression of the plane of sky component of these particular motions, and the line of sight from the comp and U comp, which actually gives impression of the line of sight oscillation. And again, we believe that these oscillations are MHD waves, and particularly the transverse wave, because the magnetic tension is the dominant restoring force. And having on to that presumption, we believe that these are the Alfvenic waves. So the key idea that I would like you guys to remember from this slide is that the corona is inhomogeneous, and I'm going to use it into my data slides and how it can actually affect the kind of estimation that we have. So the data we use is from the comp. We all know what exactly this is being. So we have also taken some of one particular sample data from UComp as well, just to compare that how the pixel resolution is going to affect the estimation. So we kind of compared the estimations from the comp, as well as we have got the estimations from the UComp as well. So we didn't use any of the polarimetry data, but we were just using the kind of the wave data, and into that one as well, only the Doppler velocity for our analysis. So again, how we can actually estimate these perpendicular correlation length. So we know that the waves are being injected at the foot point of the structure, and they are being propagating along the magnetic field. So as these waves are going to be propagating along the magnetic field, there will be not being a single isolated flux tube that is being oscillating, but like there will be a bunch of the magnetic field lines. Those are being also oscillating, and so we can choose any of the region with a kind of a reference pixel, and from that particular reference pixel, we estimate the coherence from the neighboring pixels in the Fourier domain. So what we do is we take the reference pixel and we move around, and we just keep on estimating the level of the coherence, and we end up having this sort of a coherence map. So here we have set the threshold to be 0.5. So anything above 0.5, we believe there is a significant coherence, and that is what we are going to take into analysis. Now, when we do it, you can see that we have actually got these elliptical islets of the strong coherence. So again, when we are talking about the turbulence, and if you see, imagine in terms of the hydrodynamics, you see that the eddies are basically circular in shape. But in corona, what we actually found are being elongated. Why? Because the magnetic field. So magnetic field stretches the eddies in the direction along the magnetic field itself. So these are like we have checked from the wave tracking software as well. So this is basically the direction of the magnetic field. So then we exhibit these sort of the elliptical island with a 2D Gaussian function. So we can get the estimation of the parallel coherence, and we can also get the estimation of the perpendicular coherence. So this process we can repeat for the entire corona. And when we do it, we get a map. So we have got this particular map for the coherence into the perpendicular direction, and then we have also got into the parallel direction. Now, from the
Can I interrupt for a second? Just
Sure.
ask? So what Richard was showing, so it's the same software that also gives you the direction, right?
Yep.
So you get three pieces of information: the width, the length, the ellipse, and also the direction.
Yeah.
Cool.
Yeah. So here you can see, like from the ellipse, like the scales in the parallel along the magnetic field are quite comparatively high as compared to the one in the perpendicular direction, and that is what we have been getting from here as well. So here we have got these particular scales into the direction which are perpendicular to the flux, or basically the field lines, and this is what we are getting along the magnetic field. So for the kind of the turbulence kind of thing, that how much energy is being dissipated in direction perpendicular, we're going to use the perpendicular coherence estimates. Now,
You have the same structure on this image that you zoomed in.
the same structure that I showed before.
Yes.
Yeah, it is here.
Okay, so do you have a different coherence in the counter streaming region? Or no?
Difference in the
So
perpendicular.
you have a sort of this in the parallel coherence. You have this
Yeah, so it is these. So here it is the coherence
coherent structure.
and here it is. Yes. So you can see, like, very finely, you can see that we have like the regions that's very strong. The coherence, the parallel ones are kind of very strong in some of these regions which are weak. So like it will again depend upon the geometry and that kind of thing. Again, you can see quite in here And again, for different structures, we have got the different values in there.
But I mean, that you go down to zero. Like within one structure, you go down to zero, like multiple times.
So go down in the height, you mean?
No, the parallel coherence. You see,
Yeah.
there are by the like regions, no?
Uh-huh.
So what I mean is that. So and also in the fact, so you have like a incoherent region. That's
Yep. So sure.
You have a large perpendicular coherence in the poles. Is that
Yes.
really
So
clear to
we
know
had
what's
that
going on?
bad pixels there.
So
So
that's.
yeah. So we have kind of.
But also on the left limb, is that, so that's not an open field on the left, on the this green region.
Green feature in
Around
the left limb.
500.
Here, you mean?
It's in the northeast. It could be either the way.
Okay.
Yeah. Is that an open field?
Yeah, so we do have the open fields which are kind of here. So we had got the equatorial coronal hole there, and also the closed field lines, and this was the active region. Then so I will just come on to it. Yeah.
At what point do you become limited by the spatial resolution? In terms of the perpendicular coherence line?
Yeah.
I mean, like 2 pixels, right?
Yeah.
And how big are 2 pixels in megameters?
2 pixels are basically going to be around roughly around. So for the columns, we had like around 2.2, which was corresponding to around 3 megameters, like 3,200 kilometers. So 2 is going to be around 6.4 megameters.
Okay.
I'm trying to get it just, is it a simple, what's the simple multiplying? Probably we're getting in our head right now. What do we multiply megameters by to get pixels?
Okay.
Or sorry, to get, oh, pixels, not arc seconds.
Yeah.
Okay. Another one.
Okay. So
Making life more complicated.
So on the background, we do have the data from the K4, which actually gives us an idea about how the extended fluoride should look like, just to identify what kind of structure we have been looking at. Here is the kind of the one of the samples that we have actually got, and we carried out this sort of the analysis for multiple data sets. You can see like we had data sets in 2013, 15, and 16. And we were not being able to cover the entire solar cycle because of the data gaps. And the last one we have is also coming from the Yukon, the data set. So again, these sort of the coherences, if we just plot in the probability density, you can see that most of these kind of align to be at around between 5 and 10 megameters. And there was not much of the deviation for A, for the entire sun, and B, again, looking if we just go at different times to the all of the solar cycle itself. So we can, so at this particular stage, we are still having the coherence estimates, which is the full width half max. I can just convert that one into the 1 by E folding. If I multiply this by √2, and when we do it, we can get the length scales, which what we are interested in are associated with the perpendicular coherence. So these particular length scales for the different data sets we got were being somewhere around between 7.6 to 9.3 megameters. And again, if these are full width half max, if we make it twice of that, you can get some of the scales which are associated with the supergranulation. And here comes the bit of the sciencey part. So since we knew that the correlation length scales were being estimated for quite some time using the solar wind studies and also with the Parker Solar Probe and some other methods, and again from the numerical studies, so we just compared our estimates using from the different numerical models and also with the other estimates what we actually got so far. So here on the x-axis you have got the height above the photosphere. So here it is the photosphere, and then we get somewhere around the chromosphere. This is the corona, and then we go into the middle corona, and then alpha critical zone, and somewhere over here we got the 1 AU, which is near the Earth. And here we have got the perpendicular correlation length scales. We've got around 2 models that we actually compared with. So the dashed line is the model from the Holbeck, which were published in 1986. So what they have done, they estimated that the perpendicular correlation length scale should be inversely proportional to the magnetic field. So what does it mean is that you have the flux tube, and it will go up into the solar atmosphere. It is going to expand. And as it's going to expand, that should be the scale of the correlation length scale, and that should be the scale where the largest eddies should be in. Then, but again, it was a very simplistic model. It didn't include any of the contribution from waves, from flows, or any of more complexities. It's just a simple magnetic field which is being expanded out up into the solar atmosphere. Then Kremer and Van Bullion in 2012, they have given a revised model. And what they actually did, they have got the linear expansion flux tube. So A is basically just the area of which is corresponding to the magnetic field expansion. So they have got the dependence on the flux tube expansion, but also they have got the coupling from the fluctuations, which is going to be in there, and also from the flows. When we have this sort of the second model, which is the solid line, it is giving a slightly improvised, but the higher values as we go up. And the values, what we actually got from the comp is somewhere over here, which is way higher than what we can expect from the two models. And again, so these particular models, when it just crosses the alpha critical zone, they somehow, these two more models can just kind of accompany what we have been getting estimation from the in situ spacecraft. So these plus signs are what the recent ones, what we got from the Parker Solar Probe. And so before the alpha critical zone, we only see this one particular sign, which is being published in 2005 by Spengler et al. What they have done, they actually did looking for the perpendicular correlation length scales. They have done is using the radio observations. And from the radio observations, they were trying to estimate the magnetic field. And what they found that the magnetic fields were kind of smooth to the scale of around 25 megameter. And that is what, again, when we look at the theory from the Hallweg 1986, we see that that could actually correspond to, typically should actually correspond to the perpendicular correlation length. So if you kind of ignore this particular point, which we can do in case they were not hunting for the correlation length scales. So before the alpha critical zone, so we had the only the kind of estimation. And so far we can actually come near to the solar surface, where exactly the alpha waves are being injected into the medium. So yeah.
Quick question: the data you have, which I guess is at 1AU, so the vertical set of X's on the right.
Yeah.
Here. What there's quite a wide variance there, right?
Yeah.
Is that variance due to solar cycle, or what is the variance?
Yes.
Okay.
So they had like the solar cycle, and again they try to use the measurements from the ACE and the wind spacecrafts. So what they're being trying to do is to like so in the different kind of the structure that being propagating out in the solar wind, they try to measure, and then they try to measure into the different times of the solar cycle. So that is what actually giving the kind of the range what we have.
So the one, the Matthias and Goldstein from 82, the one that's the highest,
Yeah.
you happen to know what time of the solar cycle it is and how it compares to what comp was when you were doing your analysis? I'm just wondering if you're on the high end or the low end, if that scaled and propagated from sun to earth.
Yeah.
Pattern.
So again, so having this sort of the scales and rolling back to the sun won't be that easy. That's something what we found because of this particular alpha critical zone, because that's where the kind of the physics happening, what we are not kind of very sure about. And what we believe that the turbulence is kind of kicking in somewhere, and they are being kind of changing the kind of data of that.
Okay, so then a slightly different question. Would you expect the correlation length to be bigger or smaller in an active time of the solar cycle?
You have the last part with the comp.
I mean, like we looked at the different time scales.
Okay.
And what we found was kind of more or less homogeneous.
Okay. All right.
So these were kind of like
Yeah, you're right. Yeah.
so at any time of the solar cycle, we should look like all these plots kind of overlap. And what we mean is somehow sun is structuring itself on the supergravitational scale in this order.
Got it. But it's different in the solar wind. And that's what you're saying is different.
Because like
Got it.
like as it will move out, the kind of it's going to have an expansion and that kind of thing. And that's what we think.
There's another question, I think. Yeah.
Oh, sorry. How did you distinguish between the comp and the UCOP results? Because what you're showing there is this is the resolution element of comp.
Yeah. So here we have got like this blue line. This one is what we're getting from the UCOP, and the other ones are from the comp.
Yeah, the one with the better spatial resolution actually has a larger.
Yes.
Okay.
Yeah. Yeah. So again, like we are just saying like, okay, these are the peaks that we have been talking about. And again, we are not claiming that there should be only one correlation length scale that is going to happen. So there could be more than this. But again, like depending upon the resolution and the kind of data what we had, this is what we are getting. And again, we also try to see with the other structural features as well. So recently, the Boulder Solar Probe kind of discovered the switchbacks. And the switchbacks were also having the scales of the supercapillary. So, yeah. Oh, go ahead.
And can you remind us the open field, because all the other data are in open field.
Yes.
So you're saying there's also not much difference between the closed and open structures in terms of this coherence?
Yeah. I mean, there should be some difference, but not huge. So here you can see the map. So, so here what we are having is the active region. And this particular region is the equatorial coronal hole. Sorry, I didn't use the kind of the image what I had, which was being marked with all these. And here we've got this pseudo trimmer. So again, if you see, then yes, we do find a bit of the higher in at some of the pixels. But again, mostly by looking at, because we also had an active region on this particular end, and we have kind of found a bit of the homogeneous. So
I'm just saying it would be interesting if you could isolate the open field lines and
Yes.
just look at that to compare to what's
Yes.
happening out in the open field.
yes,
Because you could have a different,
yes, you're right.
different, physics locally in the.
Yes, you're right. I agree with you.
We need to be a little careful to really look at the 3D as 7 of 8, because as Gabriel was saying, we're now really purely looking at the plane of the sky. We are integrating some of these likely not just open field, it's a mix of open field and some close field that intercept the line. So
Yeah.
that's a complication that we need to.
And not to belabor, but did you try 2018? Because it's closer to solar minimum.
We didn't have the data, which because for the wave studies, we need the continuous sort of the data. So
I think you can also measure some kind of plane of sky magnitude from the chromosesmology. Could you just do some correlation? If there's any correlations?
it's in
between-
progress.
Okay.
Yeah, we got that like from past few months when at each meeting that is something is being told. So we are working on it. Yeah, the Python code is like kind of having something, but we'll spoil it. Yeah. So here,
One
so
question about this, sorry. Is that estimation for the Alfvenic zone from one of these papers, or is that is it for homogeneous magnetic field solar minimum, or is it for where's that from?
So the Alpha critical zone is just being marked here. So like it has been coming from the numerical simulation papers. And like this is something like, so what we believe is like there's no clear defined boundary.
Yeah.
So it is between like the 10 to 20 solar radians. That is something what we just mark. Okay, then this is the boundary where the Alpha critical zone should be technically. But again, like it could be an extended region and not by like anything like that. And again, like, yes,
That's from you, is that, or is that in Zoo? Is that?
Where?
Which American? That just your.
what we say, the Alpha critical zone.
Yeah.
So it is coming from there are quite a few papers, but like mostly the one from Shar et al. And they were doing this numerical simulation and like what they call it the frothy region where they do have not very kind of smooth, but kind of fragmented kind of region. So,
Right, one more question.
sure.
Yeah, I was wondering if I give you a simulation, how easy will it for you to compute this parameter, at least in the lower part of the diagram, maybe up to 10 to the minus 1 or a little bit higher than that, kind of to see where these simulations of photosphere, lower atmosphere kind of lies in this plot.
Yeah. So like again, like for the chromosphere, we have to see like how exactly these things work. And again, we do have the data from the SSD what we were looking into. But again, chromosphere is pretty much more complicated exactly analysis, and that's what we've been thinking about. Fill in more places in this particular lab. So what we have actually got, like again, if you just scale down these sort of models, and they were getting around that it should be started in the photosphere, then it was getting something around the 0.12 megameter, which is the scale of the tremulation. But again, like when we actually go higher, which is like 1.5 megameter, this is so what we actually done is this dashed dot line is we rescale the simple model from the hallway and by a factor just to fit into that and just to see how this should actually go. And when we just scale it down, we're getting something which is way higher than it being expected from the numerical model so far. So again, the question comes in that why we are having a very high magnitude of the correlation scale as compared to what we should be expecting. So then the kind of the answer lies within the model itself. So the models were kind of assuming the homogeneous conditions. They didn't include any of the inhomogeneity that we are going to experience into the solar atmosphere. Again, these models were being designed specifically for the corona holes and also for the regions where the open field lines kind of being fan out and kind of very smooth, and that's where these kind of features are going to be. Again, the perpendicular inhomogeneity of the corona plays a kind of a significant role, which is not being included in these sort of the models. So if we do have the inhomogeneity, then the resonant behavior can actually concentrate the wave energy to the scales of the inhomogeneity itself. So it's being shown by the papers from Dave Pascoe and also very recently by Robert Mega and Daniel Soray. What they have actually done is they have got these the velocity fluctuations, and in the numerical model, they actually kind of go out gradually away from the solar surface. And when they actually do it, then due to the inhomogeneity itself, these wave energy kind of concentrates to the scales of the inhomogeneity kind of being injected into their model itself. And again, most of these numerical models that we had actually compared with, they didn't have the role of any other Alfvenic wave role. So they simply had the transverse fluctuation, the Alfvenic fluctuations, and the recent one only had the flows. And so yeah, so the models might at some time include more of the physics, and we can be able to see that if they can be able to match what we have been getting from the observations. So again, here what we have actually got so far is basically from the UCOMP and the COMP estimates. We got the higher magnitudes as what we should be expecting from the micro models, and between 1.3 to 1.05 solar radii, we got the scales which are compared to 7.6 to 9.3, which are comparable to the supergranular scales. So supergranulation is kind of the energy injection scales into the corona are compared to these particular scales. We believe the inhomogeneity and the resonant behavior can actually lead to the concentration of the wave energy at these particular scales. But again, we need to see more. These may have some sort of this implications that it comes down to the shock versus the heating, the mechanisms for the corona. And again, so again, if till now, if everything is going for the guessing, we have got some estimates that the numerical simulations can play around with. This is Thank you.
We can have more time for a quick question.
So, infinite resolution, would you expect the injection energy? Would you expect to find evidence of injection energy at smaller than supergranular scales, or you think there's a cutoff at that point?
Technically, there shouldn't be one single correlation length scale or the energy injection scales. What we have been getting is like a kind of a distribution of these. So there could be like this is like what I'm again saying, like depending upon the resolution what we have got, we have been able to see this. So maybe if we can be able to get high resolution data, maybe TKS people can actually help us with that. So maybe we can be able to estimate of the correlation length scale, which might be lower than these ones. So the energy injection may be happening at different scales in different kind of the topologies we have been looking at. So you. Yep.
All in this next, I would just say, but I then maybe so I'm just pointing at
Yes.
all and then are my next two talks. Did you have a question?
Oh yeah, no, I had a question. So you're saying it's getting little lengths, you're getting a spectral distribution of lengths. Data have we see the combination of along the lines, like get that what you're That's what you're hoping. That's,
Yeah.
well, that's a cool result. So the information is somehow preserved, but it's out in the spectrum.
This result's been published, right? I think this is the first publication using data, I believe.
Yeah, it will out on Monday, I suppose.
I remember that. Yeah. It's the first one. Thank you, guys.